All right, I think we'll start. Hi, I am Erlend. I'm from Norway, and I'm here to talk to you today about modern web application security bugs. So a few words about me first. I work for a small consulting company in Oslo, and I usually work as a developer, but I also do security stuff. So I do security testing, I do security architecture, and I've also started doing quite a lot of bug bounty hunting. As you can see, I also built some open source security tools, and I'm also head of the OS Norway chapter out of Norway, and you have my Twitter handle there as well. If you want to ask me questions later or during the talk or whatever, just raise your hand if you have any questions during the talk. The OS Top 10 has been out for quite a few years, and one of the sad things about the OS Top 10 is that we've seen the same bugs appear over and over and over again since one of the first ones came out. But as I started to look into all of these bug bounty programs and looking through what was happening in these bug bounty programs, I could see a lot of new types of bugs that were appearing that didn't really get any focus because a lot of people are just focusing on the top 10. So we had a new version of the top 10 come out in 2017, and on this list were two new bugs, or three actually, but two of them were kind of bugs, and the last one is more of a process thing. But we had XML external entities and insecure deserialization come in. And these are things that we've seen in these bug bounty programs for a long time. So what I'm going to do in this talk is I'm going to go through, I'm going to start at some of the new stuff in the OS Top 10, and then I'm going to move outside the OS Top 10 and explain some of these bugs. And I'm either really brave or really stupid, because all the things I'm going to show you is mostly demo-based, and I don't have video backup because I don't believe in that. I'm demo or die, so that they better work. So if we go to the bug bounty programs, we'll see a lot of the same things. This is a statistic from BugCrowd, and we see a lot of the same things like we see in the OS Top 10, like cross-site scripting is fairly dominant. We have stored cross-site scripting and reflected cross-site scripting here. And we have some other things like server-side injection and then a big pile of other over there. If we go to HackerOne instead and their report, we'll see that at the top here, it's a bit hard to read, but it's also cross-site scripting. That's the top one. And then we have information disclosure as the second one. And we can see they've also divided this into industries. So we can see that transportation, for instance, over here, they have a big problem with cross-site scripting. One of the things that I've really had a lot of help from when learning about these bugs is to read reports coming out of these bug bounty programs. So this is a Twitter account called Disclosed Edge 1, which will tweet out any new report that comes out from HackerOne. And in these reports, you can actually also search them or look them up on HackerOne. They have this list as well. But on each of these reports, you can go in and you can find what was the bug about, and often they'll share a lot of details about how the bug was found, etc. This is one of my bugs that I found in a library called Samlify, which had an XML signature wrapping vulnerability in it. I'll show you some of these reports throughout this session, so you can see some examples of the things I'm talking about. So the first thing we'll start talking about is XML, and I mentioned XML external entities, let's jump straight into the demo. So I have this really simple API. The top box here is the request that I'm sending, and the bottom box down here is the response I'm getting back from the server. And this is actually happening, so I'm not faking it. It's actually being sent to the server, and I get something back. So you can see if I click this multiple times, the only thing that's changing is basically this ID field in the center here. I can also get the data back, not that interesting, but now we're moving into the XML external entity attack. So what I'm doing in this case is I'm defining a new entity called content, and the content of this entity is going to be the contents of this file called etc password. And then I'm going to use this new entity down here. So let's see what happens. It grabs the contents of the file and it pushes it into the XML, and that's stored in a database. So now instead of a simple name or something like that, it grabs the content of the file, pushes it in. And because this backend is a Java app, I can do more than that. I don't actually have to have the file prefix here. I can just remove that. Still works. But I could also just do a dot. If I just do a dot, it's going to list all the files in the current directory that the application is running. And I see there's a file here that looks interesting called passwords.txt. So let's grab that. And the password was then summer 2018. These kinds of passwords have been mentioned many times in security talks lately because people tend to switch passwords in this pattern where they add the year as a prefix. So this was the base version of this. We can list files, we can grab files, we can steal stuff off the server. Now, the next part, we have what's called an XSLT. And an XSLT lets us take an XML and then transform that XML into something else. In this case, I'm transforming an XML into HTML. So you can see down here, now I have an HTML, I have body, and I have a table. And I just took the values from one of the previous messages that I sent in and just converted it to HTML using this XSLT. But that's not all that interesting, but of course I can use this because XSLT provides a lot of features. So if I can provide my own XSLT, then I can actually start to query the system about things. So in this case, I'm going to ask it what version of XSLT is here. So you can see here, it says this was version 2.0. This is the vendor of this XSLT transformer. So you get a lot of information that's just leaked back because I can do this. There's also an interesting property called, or a function actually called document. So with document, I can take a file, an XML file that sits on the server and include that in the XML. So much like the XXE that I just showed you. But in this case, it has to be an XML file because if not, it wouldn't be able to parse it. So in this case, I'm stealing a file called pom.xml, which is basically the deployment descriptor for a Java app. It will contain all the dependencies. So if we scroll down here, we can see that it lists out all the dependencies that this application is using. Of course, I could also do XXE in the XSLT because the XSLT is also an XML. So in this case, I'm just doing the exact same thing as I did in the first example, just stealing the contents of this file. It doesn't have, in XSLT version 2, it also provides a new function called unparsed text. And in this case, it doesn't have to be an XML anymore. It doesn't have to be valid XML anymore. So I can steal any file off the server. I can just do like this. And again, I'm stealing the same file, just as an example. I could also do lookups across the network. So now I can start to do HTTP queries, for instance, from the XML parser. So the XML parser will go and look up this URL that's here. And this, if I just open it, we'll see that what's behind this internal URI that I can't reach from the outside is actually an Elasticsearch instance that's supposed to be hidden. But I can reach it because I'm using this abusing this functionality, basically, to get stuff that I'm not supposed to be able to get. Sometimes when we're abusing an XXE vulnerability, we can't see the end result coming back to us. Because maybe it fails, like it fails to parse it, or it doesn't really show us the XML that it got from the parsing. But in this case, we can use something called blind XXE. So this is a bit more difficult to explain. I'm just going to show you first, and I'm going to explain what happens afterwards. So first, I'm going to set up a server that basically gives back a file. If the parser tries to go to my server, it's going to get this file that contains the data that you see there. And what it's going to do, it's going to grab the contents of this passwords.txt file. It's going to send that back to me on an HTTP request. So if you see what's happened when I click the send button, there's first a GET request that comes and gets this file, this ext DTD file that's on top. And then there's a new request coming in that says steal, and then we see the password once again. We see the password summer 2018 here. So to briefly explain what's going on, so I'm just going to close this one. What we're doing here is first we're defining a parameter called data, and the contents of data is going to be the contents of a file. In this case, etc shadow. In the next line here, we're defining a new parameter which we're going to grab from my attacker server. So we're going to grab this DTD that we see at the bottom here. This DTD it contains a new entity called external entity, which contains this stuff, which basically at some point will try to get something from my server. So this is where the data is leaked. So it loads the DTD, it adds all these things down here, and it ends up sending the data back as a new GET request towards the end. It's a bit more difficult than the other ones where we could just see the data coming back immediately, but it's also super scary because this parser might be way down in the stack somewhere where we can't even reach it, but suddenly it starts to ping us back. So this is an example from HackerOne. In this case, the program is run by Twitter. The severity of this XXE report was scored as a medium, 5.3. But the bounty that the guy who found this got was $10,000 for this. So it's quite a big sum of money. Because, of course, this is a really serious issue. If you can steal any file off the server, you could steal things like SSH keys or other passwords or things like that. So it might end up giving you access to the server. So how do we stop it? Well, there are a few alternatives. We could disable DTD support, so you can't define these entities at the top of the XML. So that's the first thing that we want to do. Some frameworks have this feature called secure XML parsing, which will basically do the same thing. And then we can also disable external entities. There are a lot of different ways. If we go to the OWASP XML external entity prevention cheat sheet, we'll see a lot of examples on how to do this. Luckily for .NET developers, XXE has been disabled since version 4.5.2, so this is quite a long time ago. But yet we still see developers re-enabling it because they need some feature for some reason. In Java, it's just disappointing. There are so many parsers that are still vulnerable to this, so you have to make sure that you secure it. I would actually recommend that if you have an XML parser, try it out, add a unit test so you're sure that it's never reintroduced later at some point. So that was XXE. We're moving on to the next bit. So we're moving on to the insecure deserialization bit that was also in the OWASP top 10. And serialization is something we're doing a lot. We are serializing objects into JSON or XML or some kind of binary format to pass it across the wire, to store it in a database and things like that. Deserialization is, of course, the opposite. We take this serialized object and then we convert it back into a format or an object that we have on the server. And this is used in all kinds of places. It's used in IPC stuff. It's used in all kinds of APIs. It's used for caching. It's used for shared caches. It's used for databases and all kinds of things where we're passing objects back and forth over the wire. So we can imagine it looks something like this. So we have some kind of a JSON writer class that's going to take an object and then it's going to serialize it for us into JSON. And then at some point later, we're going to read it back in and we're going to specify the class that it's supposed to create. And we're going to read stuff in and just create a new object. And this is fine. Like if we have the top object here, this is fine. Like we have a class of person. This class has a name. And it has a constructor that takes a name and just basically creates an object that doesn't do anything other than hold a tiny piece of data. If we look at the second class here, though, if we were ever able to instantiate that class from an API call, this would actually run a file because it does work in the constructor. And this might be a utility that we have somewhere, something that we're not supposed to use from the API, but sometimes we're able to instantiate those objects from the API regardless. So some of these frameworks, JSON frameworks or XML frameworks, they allow us to specify the type that we want to get back. So maybe the API is supposed to take in a person, but in this case, we have this $type thing where we can specify, well, I actually want this runner class instead of, so I want this class up here. I don't want the person object. I want to instantiate this type of object instead. And if this feature is enabled in the framework, it's going to start this class and it's going to run the code. Same thing here for XML. We have this type parameter. It might be called something else, but you'll see it because you'll see like package names and things and maybe even like which DLL it's supposed to be in. And this would, again, allow us to instantiate an object that we're not supposed to be able to create from the API. Usually, these things are a bit more complicated than this. So this is one example from .NET, from the presentation framework. So in this case, you can see the $type, and we're creating an object data provider. And within this object data provider, we're creating a process, and we're taking this process and we're adding some parameters to a method, and then we're invoking that method. So usually we have to chain a few objects to get where we want to be. So because of course, as an attacker, we want to be able to run code on the server. So here is an example from Spring. And in this case, instead of specifying the type like a parameter, we're instead using something called a dynamic proxy. And we're saying, this is the interface of the class that you're going to create, but the class itself is going to be completely different. So in this case, it's just going to do a ping. So if I send this, it seems to fail. I'm getting like a 500 server error back. Oh, man, it didn't work, right? But if we look a bit further at this message, we can see all the way over here, it says class cast exception, and then there's a Unix process at the end. So it actually did create a process. It did actually run ping, but it wasn't able to convert that into a contact. So that's why it failed, but it actually did run what we're supposed to run. So, but I mean, ping, that's not all that interesting. What if we could get access to the server instead? So let's try that. So what I'm going to do in this case is I'm going to run bash. And I'm going to give it a command that is going to run. So I'm going to create an interactive bash shell. I'm going to send that to dev TCP, a host name and a port. So it's actually going to open a connection outwards toward my attacker server. And it's going to create a remote bash shell towards my server. But for that to work, I would first have to set up something that listens on that port. So I'm just going to do that really easy using netcat. So I'm going to listen on port 1337. And then when I hit the send button, you see there's a new prompt that appeared here. It says root on contacts hackable victim. So now I can actually run commands here. I can do ls, I can browse around the file system. I have full control over this server, so I've just hacked into it by using deserialization attack and then gotten a shell back to me. This is pretty scary. Here is an example from HackerOne. This was in Starbucks, the Starbucks program, and someone found a remote deserialization vulnerability in one of their systems. They had something called a JBus MQ, which is a message queue, and this one was vulnerable to deserialization attacks. Things that can happen with these types of attacks, like a lot of the documentation and blog posts around the deserialization attacks have been focused around things that are across a specific framework, for instance, like the presentation framework that I just showed you. But what if someone could instantiate bad utilities that we have? What if they could instantiate more than one singleton of a class we expect to be a singleton? What if they could instantiate this util method, the runner method, or the runner class that we had? What if they could do things that they're not supposed to be able to do? So we might have, even though our frameworks might not be vulnerable, we might have classes that are dangerous in our code base, and an attacker might be able to instantiate those objects if he knows what he's doing. And of course, this can lead to all kinds of stuff. This can lead to denial of service because we might be able to shut down the server. We could manipulate the state in the session, things like that. We could compromise the integrity of the system, or we could even, as I've shown you, get remote code execution. So the underlying cause is usually that the attacker is somehow able to specify the type. So the class that's supposed to be instantiated is in the attacker's the attacker is able to specify that somehow and then get that object instantiated. And the way that we can stop this is, first of all, we should keep our frameworks up to date. I've put that at the lower one because it's, but it's kind of the most important one because a lot of these things are being patched in frameworks. But we also want to limit deserialization to specific packages or specific namespaces where we have our API contracts. We want them to have certain annotations for them to be able to be instantiated by the deserialization framework, things like that. And if we can, we should really disable specification of types. Like in JSON.NET, it's disabled by default, but you might be able to turn it back on if you need it, but it might be dangerous. So the next one is something called template injection. this wasn't in the OWASP top 10, and it's not listed as a specific thing, but then the top thing in OWASP top 10 is injection, which covers a lot of stuff. When people think about injection, they usually think about SQL injection, and this is something quite different. So we have these templating frameworks. We're using these fragments, and we're creating HTML in some way. This might be something we do on the server side with something like Razor, but it might also be something that we're doing on the client side using components from React or Angular or Vue or something like that. So we have these templates. These templates are used to create HTML, and we kind of combine these things, and this simplifies our architecture, of course. But it might also be a bit dangerous. So at least some of the first types of templating frameworks, they were quite, the implementation was really basic. Like, so if you had a template looking something like this, what would actually happen is it would parse this, and it would run something like this. So it sees, okay, there's an H1, and then there's like these curly braces that signifies that here I'm going to run some code. So it splits it out into 2 strings, and then it runs eval on the thing in the center, which might be okay. I mean, this is a template provided by us as a developer, but it might also be dangerous if we combine these things in the wrong order. So here's an example. We have a variable called title, which contains hello. We have a simple template, the same template I just showed you, where we have title as a variable. And then, of course, when we invoke the render function of the templating framework, it's going to render h1 hello. Perfect. But sometimes we want to take a few templates and kind of combine them into a larger page, because we might want to reuse some component of the page in many different places. So we might render one thing in one part of the code, and we take the output of that, and we shove it in to another template further down the line, and we end up with something like this. And the thing is, as a developer, this works perfectly. So we have title is hello, and body is world. And after rendering the first bit, it's going to be h1 hello h1, and then we put it in the second one, and we render that, and it's going to be hello world, just like we expected. But there's an issue here. What if the variable in the first template contained a new template? So what if it contained, instead of hello, it contained 2 times 2 inside curly braces? In this case, it would render the first template. It would come back out as a new template. So you can see in this line here, we actually have a new template, which is the contents of the variable coming from the end user. And then the end result is we're going to actually eval the stuff that's inside here coming from the end user, and we get 4 here instead. But seeing code like this is boring, so let's do a demo. I have this simple application. I can send in I have a URL parameter called name, and I'm going to send in my name. And what you see here at the top is the rendered HTML, and at the bottom you see the source code of this rendered HTML. So in this case, it just says, hello, Erlend, and then you can see the same thing down here. It says, hello, Erlend. Now, what happens if I, instead of typing my name, I type 2 times 3? Now it says, hello, 6 instead. And it says hello, 6 down here as well. So in this case, we have a template injection. So I can provide a template either as a part of the URL or as a post parameter that's stored in a database or whatever, and it's going to be rendered on the server side. So I basically can run code on the server. So this system that's running this is using a templating framework called Twig. So if I do _self, it's going to fail, and it's going to actually reveal what type it is, because it's going to say Twig environment here, and it's going to say Twig template up here, and it fails. But now I know it's Twig, so now I can start to mess around with it. And I'm going to do the exact same thing as I did with the insecure deserialization. I'm going to use a vulnerability that exists in Twig, which is I can define a filter called exec, and this filter is going to call a function called ID, or a system utility called ID. So it's going to exec ID, which basically means it's going to run the ID command on the server, and it's going to print out whatever was there. So in this case, it says, well, this application is obviously running as www.data. But instead of running ID, I'm going to run this bin bash c blah, 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 and then just do the exact same thing as I did with the insecure deserialization. So I'm going to set up a new listener, like this, and I'm going to send it in. And as you can see, I now have a shell here on this server. And I'm now logged in as --data, and I can run commands just as I did in the previous one. Now, this was server-side template injection. So you could see when I just had 2 times 3, it would come back as 6 down here. But what about client side? So we have templating frameworks on the client side as well, things like Angular, for instance. So in this case, I'm going to send this, but I'm not going to render it wrong on the server side. I'm going to render it just as a normal template. So if you look down here, you see it still says 2 times 3 down there. But as the rendered HTML, it says 6. So obviously, something's now broken between the lower one and the upper one. So the rendered HTML is showing something different than what's down there. And the reason is, of course, that there is Angular is being invoked here. And Angular sees this 2 times 3 template down there, and it thinks, hey, I know this. This is an Angular template. I'm going to execute it. And hence we get the 6. Of course, if we're thinking now, we could do cross-site scripting. So instead of doing 2 times 3, we could do alert 1 instead, just like a normal cross-site scripting example. Unfortunately, in this case, that wouldn't work, because in this version of Angular 1.0.8, it had a sandbox. So it said, you're not supposed to be able to invoke a specific set of APIs from templates. But it also had a vulnerability that allowed you to get around this restriction. And this is a bit of an odd one. So instead of just a normal, instead of just like trying to invoke the alert function directly, what we can do is we can take a string, and we can take the constructor of the string, which is the string constructor. And we can take the constructor of the string constructor, which is the function constructor. And we can take the function constructor, and we can provide it with a new function as text. And then we can invoke that function. So this was a bypass of the sandbox that was in Angular. So if I send this in, I'm going to get this annoying pop-up, and it's going to pop up twice for some reason. This was a way to get around this restriction. And the interesting bit that you can see here is if we look all the way down here, we can actually see that this is HTML escaped. So the server-side framework tried to do the right thing and kind of escape things, or you're not supposed to be able to go in and out of JavaScript and things like that. But before Angular sees this code, it's going to be de-escaped by the HTML parser, because it's going to say, OK, there's this text inside this element, and I'm just going to take that out. I'm going to give it to Angular, and Angular says, hey, there's a template. Cool. I'm going to execute it. So here's an example of Angular injection from Rockstar Games. It got a bounty of $1,000 in this case, and it was rated as high. So an example of the same thing that I just showed you. So if you want to test for template injection, you can try all kinds of templates. So if you know what kind of framework you're using, you can try to inject templates that work for that specific framework. So either double or triple curly braces. It could be like $1 and then curly braces. It could be all kinds of things that's specific. And I usually test with things like 2 times 2 or 4 minus 1 and things like that, because that will easily show if something is working or not. I will see what I get back. And if it's the same thing, then it's probably safe. But sometimes it doesn't render the template exactly where you are, but once you're clicking around, you might find that at some point later, it does actually render it because they're like jumping outside of the component or something like that. So we can use this for cross-site scripting, like I just showed you, and we can also use it to get remote code execution and run stuff on the server. If we want to stop template injection, we have to make sure that we don't double evaluate templates. So we don't take the contents of one template, render that, and then we put that into a second template, and then like string concatenation thing, and then create another template from that, and then run that all over again. And then when we have when we're using client-side templates, we have to make sure that the server doesn't give the browser a template that it's not intended to do. And this was actually in the Angular documentation for a long time. Do not mix client and server templates, it says at the top point here. In the last versions of Angular, they actually removed this sandbox altogether because there was a group of researchers that were trying all the time to break out of the sandbox. So whenever Angular patched the sandbox, they would go back in and find a new way to bypass the sandbox. So at some point, they just said, we're not going to have this sandbox anymore because it doesn't make sense. You shouldn't mix client and server templates anyway, so we're going to just remove the sandbox altogether. So then you could actually have done alert 1 if that was the thing that you want to do. The next thing is insecure CORS, or cross-origin resource sharing. This is also something that we've seen a lot during the last years. A lot of developers seem to kind of misunderstand what this header is doing, or they kind of forget that they deployed something that was really permissive, and it ends up in production even though it was just meant for test. But so we have these headers that will allow the browser to read stuff if it's set correctly. So I asked my friend in Google Translate to help me understand what this header is doing. So we have, as the first example here, access control allow origin example.com, access control allow credentials true. And I'm going to translate that from HTTP to English. And it's going to say, OK, so if the user is logged in and visits example.com, please allow that site to access the user's data. OK, so we really have to trust example.com in this case if we want that to work. What happens then if I do access control allow origin star, and then access control allow origin and translate that? And it's going to say, well, if the user is logged in, please allow any site that the user visits to access the user's data. That doesn't sound good. Luckily, the browser vendors knew we were going to mess up this one. So you're not actually allowed to have a policy that says access control allow origin star and then allow credentials true. So this is what you'd see in the browser console in Chrome, for instance. It's going to say, well, this is not allowed. Sorry, you can't do that. But as developers, we are creative, so we've found ways to mess this up anyway. So the common mistakes, the echo, that's the first one. So you can't have star. So people figured out, well, I can just take the origin header coming into the server, and I can add that as the access control allow origin header going back as the response header, and it will work. Yeah, you now re-enabled access control allow origin star, and you really shouldn't have done that. And this is something we've seen a lot. The next one, insufficient validation. So origin, request get origin header. And if origin ends with example.com, then we're going to add this. So we're not going to add just any header, but if it ends with example.com, that's fine. Except not example.com also ends with example.com, but it's not example.com. Third one is null. What is null? Well, access control allow origin null. Access control allow credentials true. Null. We have to ask Google Translate again about this one. So access control allow origin null. I'll translate that. And Google Translate says, well, if the user is logged in, please allow any site the user visits to access the user's data as long as the site knows how to use iframe with the sandbox attribute. OK, here's an example. So we have an iframe with a sandbox. We say allow scripts, allow forms, and then in this iframe, we do this request to the server, this XHR request. In this case, it's going to get the null origin as its origin. And so we've kind of once again re-added this allow origin star, allow credentials true. A lot of this stuff was found by a guy called James Kettle. And James Kettle works for Portswigger, which creates the burp suite, which is one of the best pen testing tools for web applications. And this is one of the bugs that he reported. And as you can see, this was reported to Zomato. And down here, we see the exact pattern that I just showed you for one of them. It will allow anything ending in zomato.com, including not zomato.com. So this was the exact same example. Next one, server-side request forgery. What is server-side? You might have heard of client-side request forgery. What is server-side request forgery? Well, a server-side request might be a reverse proxy. It might be something in our system that once we send in a request to do something, that system is going to do another request to get something else. So we might do an HTTP request to some kind of system, which might be a server application, it might be a Nginx, it might be some other type of reverse proxy, it might be whatever. And then based on that request, the server application will then do a second HTTP request to get some data somewhere else. So this might be from a microservice, it might be from some service out on the internet, it might be something completely different. But anyway, the thing that where this can be a problem is if in the first request we can modify the location of the second request. So here's a simple example. So we have a request from the browser that comes in, and it's example.org/images/200 by 200/product.jpg. And in our server application, what we're doing is we're taking the original URL and we're extracting, we're removing the first part, and we're putting in a new server, which is http images.example.org instead. And then we're going to get that, and we're going to stream that back to the end user. So we're deleting the first part, adding something new, and then we're going to grab that data and stream it back to the user. The problem in this case is, what if we do something like this? Well, it's going to delete the first part, and it's eventually then going to go to images.example.org.evil.com. So by modifying the first request, we can now specify a new location for the back channel request. So this is server-side request forgery. We can now make the server do a request that it didn't intend to do. So there are many ways of doing this. This is another example. Instead of just specifying a domain name, we could specify an IP. In this case, we do. This will become basically basic auth. So it becomes the first part, images.example.org, becomes the username, dummy becomes the password, and then @ and then the IP that we actually want to go to. That's another trick that some people do. Some systems, they have this thing where they want to import data for us. So this might be like an RSS feed, but it could also be like financial data or something. So we can have an XML file somewhere on our site, and we can make their system go and read that data for us. So this would be a typical example where we could see something that would load something that wasn't supposed to load. So it could do something like this instead. So instead of going out and grabbing the data that it was intended, we're going to go to localhost. And we're going to go to the MongoDB database that sits on localhost on port 27017. And we're going to read data off of that instead, because we can now make requests wherever we want. Or in some cases, we could even abuse this to read files, like we did with XXE. So we could use a file URL. It would go read the file instead of going to an external URL. But where this has become very interesting is in cloud providers, because a lot of cloud providers, they have this host at 169.254.169.254, which is called a metadata host. And this is a place where you can go to get information about the current cloud server, but you can also get, in AVS, you can also get security credentials. So we could use this to get security credentials back to us, then we might be able to SSH into the server. And of course, we could access all kinds of other systems there as well. And this is hard. Like, protecting against this is really hard. Like, let's look at IP addresses, for instance. This is from the slides of a guy called Nicolas Grégoire, a Frenchman who's been doing a lot of research into this. So okay, so we have 169.254.169.254. This is the same IP, 425. Hey, that's above 256. What's going on? Well, a lot of frameworks, they will just like do mod 256 if the number is too high. So this is the same IP with overflow. This is the same IP, just numeric. This is the same IP with numeric form with overflow. This is the same IP in hex format. This is the same IP in hex format without the dots. This is overflow in hex format without dots. This is octal IP. So instead of this, in the 10 system or 16 system, we were in the hex, we're now using 8, based on 8. So there are all kinds of formats. This is the same thing. It's octal mode, but in this case, we have overflow or a lot of zeros. So this can be quite confusing if we're trying to parse this correctly. We could also use domain names. So we could create our own domain name, custom.evil.com, and we could point that at 127.0.0.1. So it looks okay, or well, evil.com doesn't look okay, but if it looked like a little bit more benign than that, so the server would try and would resolve that and would get, oh, I'm going to go localhost. I'm going to grab some stuff out of there. So someone actually set up a service for this. So if you do 127.0.0.1.zip.io, that's going to resolve to the IP in front. And you can base 36 encode it as well. So in this case, it still resolves to 127.0.0.1. And we can add stuff in front of that as well to make it even more convoluted. So 0.0.0.0, that's like all interfaces. It doesn't have to be 127.0.0.1 either. It can be 127 4 times. It will be the same thing. And of course, in IPv6, we get all these kinds of new things, like a different format for localhost. We get, yeah, you can see them here. So there are all kinds of ways of specifying the same IP, and blacklisting this can be quite hard. And then there's a guy called Orange Sai, who's been doing a lot of research lately into like URL parsers. And he found that, like this URL here, it would be parsed differently depending on if it was parsed on Windows or Linux. So on Windows, it would see the whole thing as one path. But in Linux, it would see the first part as the file, and then what comes after the question mark would just be disregarded. And of course, there's Apache Tomcat, which is quite common in the Java world, which for some reason lets you specify ... semicolon, and it would treat that as it was /... because why not? So you could use this to do path reversal and get access to things that you're not supposed to be able to access. So here's an example of a SSRF, server-side request forgery, once again from HackerOne. In this case, if we see all the way down here, that's the exact same IP that I just showed you, like 169.254.169.254. So this is a perfect example of that AWS IP. Some of the cloud vendors, they now require that in order to be able to reach that host, you have to specify a custom header. And that's supposed to protect against this thing, because then you wouldn't necessarily be able to add a custom header when you're doing an SSRF attack. How can we detect that this thing is going on? Well, we could do something as clever as building an egress log. So whenever we have a web client or some kind of outbound request, we could log all of those. So just like we have an access log for inbound request, we could also have an egress log for outbound requests. So we could search that from time to time and see if something bad shows up. Or we could have like a whitelist or something in there. So another way of protecting against this is we could use an outgoing proxy. So instead of doing all the requests from our server, which sits maybe in a network zone with access to a lot of things, we could say, well, if you're ever going to do an outbound request, well, we're going to do this in a different network zone where there's only this proxy server and it can only go outside. We should, of course, normalize the host name, so we could resolve it to an IP, and then we could either use firewall rules or some other way of doing a whitelist or blacklist-based approach there. IP tables or something like that. Next one is something called Subdomain takeover. This is a guy called Franz Rosen of Detectify who did a big write-up of this, but there's been a lot of these lately. I'm going to show you a quite recent example of this. So what this does, it exploits that we sometimes configure DNS to point to places, and we forget that we did that at some point, and then someone else can take over one of our subdomains. So for instance, in Heroku, we can specify our name as a part of the URL for the Heroku app. In AWS, we can also have our name as a part of the URL, but it's still like an Amazon domain. Like this is the top-level domain. So maybe we've set up a DNS entry to point to one of these, and then at some point we just remove them, and we forget all about it. So Detectify, they found that there were over 100 different cloud services that had these kinds of options where you could specify your own domain as a part of this. So let's see an example here. So let's say OASP.herokuapp.com. So the company that owns this thing, they're going to go in and say, well, this Heroku app is going to have a custom domain name, which is going to be oasp.example.com, because that's our company domain, top-level domain, example.com. And then we go into our DNS and we say that if you get the IP of OWASP, or you get a lookup for OWASP.example.com, then you're going to go to this Heroku DNS thing instead. So to show it as an animation instead, so we're going to go out and say, hey, I want to know the IP of OWASP.example.com. And it's going to go to the DNS of example.com, which is going to say, hey, you should go over at Heroku DNS and ask them instead. So you go over there, and you get an IP back, and then you can go and reach the actual service running on Heroku. And everything works fine. But then at some point, we remove this Heroku application, but we forget to fix the DNS. So the attacker can now go in and recreate an application with the exact same name, and they can now own our subdomain, because in our DNS, we still point to this thing, even though we removed it. So this can have quite a big impact. Like if an attacker can control one of our subdomains, this is perfect for phishing. Now you actually have a domain that belongs to the company that you're trying to phish. You could use this to inject cookies, domain-wide cookies. You could do defacements and all kinds of things like that. And you could even create HTTPS certificates for this subdomain. So here's one example, a subdomain takeover on s3.shopify.com. Here's a very recent example. Microsoft had this domain that they were using for Windows tiles. So this is from, it's quite recent, April 17. And they forgot about this domain, or they forgot that they had the DNS entry pointing to an Azure service. So the host that should deliver the XML files, notification.build.mypinned-site.com, only showed an error message from Microsoft's cloud service Azure. The host was redirected to a subdomain of Azure. However, this subdomain wasn't registered with Azure. So a guy called Hanno Buck, he went in and he registered that domain, and now he kind of controlled this thing that was used to display data on tiles in Windows, which is kind of serious. But he did it to block it, and then reported it to Microsoft. Here's another example. It's a bit, the text is a bit small, but what it says here is, this is from cert.sh, where you can look up in the certificate transparency logs, like certificates that have been issued by the CAs. And in this case, a certificate was issued with the domain name Simon Grushki has hacked prod2.uber.com. Because he was able to do a subdomain takeover for prod2.uber.com, and then he used some domain service here and created a certificate for the thing that he hacked, but he added like this I have hacked it.com to the beginning. And this is going to stay there forever because the transparency log is going to, it has to show all the certificates that's ever been issued. So if you go and search, you'll find it. The next thing I'm going to show you is something called web cache poisoning. And this was also something that James Kettle, which I mentioned earlier, found when he was doing some research. He was looking into bugs that were hard to exploit. So maybe you could, as a user, you could send something in and you would get it back, but you couldn't get any other users to see it. So if maybe you could like do a self-XSS, a self-cross-site scripting attack, but you couldn't get any other users to see the stuff that was injected. So you could basically only attack yourself, which is kind of annoying if you're trying to do a cross-site scripting attack. So he was looking at this, and he was trying to exploit these unexploitable bugs. And he has written a blog post about this and presented it at Black Hat a few years ago. So let's look at how this works. So we have our server. We have a proxy that sits in front of it. This might be our own proxy. It could have been something like Cloudflare or some other type of proxy that sits in between. And then we have our clients. So the first client comes in. He asks for some website. It's not in the cache, so the cache goes back and it goes to the server and looks up the data, stores it in the cache, and returns it to the client. So when the next client comes along and asks, there's going to be a hit in the cache, and the data's going to go back. So everything works as this is how a cache is supposed to work. But then what if the attacker is able to call this URL with this attack, then have this go to the server, and the server has some vulnerability in this case. So the attacker sends some malicious data into the server does something stupid with it, renders it in a way that maybe becomes a cross-site scripting attack, and then that's stored in the cache. So when a benign client comes along later, this client is going to get the poisoned version, the one with the attack in it. This is what James Kettle was researching. And he found a lot of ways to do this because of frameworks, because of how caches works and things like that. So in this case, I have, at the top here, I have a simple request that I can do. It only has 2 headers in this case. It has the get/http11 and it specifies the host header as well. So if I send this in, I get back 200, OK, and I get this URL here. This is the important part in this case. So you can see it says www.hackable.network here. And that's the same thing, that's the host of the actual server in this case. So if we go over here instead, it says attacker.com, and it says x-forwarded host. So this is a new header. And if now I'm the attacker, I'm going to try to poison the cache. So if I send this in, we now see that this thing was changed. So now it doesn't say www.hackable network anymore. It says attacker.com there instead. But our benign client still sees the benign version. But we poisoned something with the URL parameter. So we poisoned a cache that wasn't the same that the benign client was asking for. So we removed this, and we tried to send it in. And now you can see down here, it still says www.hackable network. So I'm going to send this in a few times, because we have to wait until the cache expires. And at some point, if you look down there, you're going to see at some point it's going to change. This is when the cache expired. You see that? It expired. So now if I go back here and I send this request, you can now see that the benign client also got this poisoned version. How brave are you guys? Are you brave enough to participate? If you are, you can go to this URL. I'm not going to do anything harmful. So if you have a phone or a laptop, you can go to this URL here. If you open it, I'm going to open it in a new tab here. It will, see. Yeah, it will look something like this, right? So it's www.hackable.network. It should look something like this. You should say welcome, and then it should be a big NDC Minnesota link or a picture there. You see it? Yeah. Now I'm going to try to poison it. So all I'm doing now is the web server, or not the web server, the browser is now hammering this thing. It's hammering this thing with requests. I'm not changing anything on the server. If you try to reload the page in your browser now, you should see something different. So I didn't change the server at all. I only poisoned the cache. So it should now look something like this instead. So that's cache poisoning. And it's quite it can be quite a bad problem if we have this. So these are some of the headers that James Kettle identified, like x-host, x-forwarded host, x-original URL, and x-rewrite URL. So these would be used by frameworks in ways that they shouldn't. And we could use this to poison different URLs. And he has some really cool example applications that you can try if you go to his blog and read on his write-up on this. It can be hard to do this attack correctly because we have to figure out which URL parameters are part of the cache keys and things like that, and which headers are part of the cache keys. But James Kettle, working for Burp Suite, he added a new extension to Burp Suite called Paraminer, which can kind of automate this stuff. So if we want to stop it ourselves, we should probably block these headers if they're coming in from the outside, like x-forward host, x-host, et cetera, if we're using them, that is. We should stop them from coming in because they're not supposed to come from the outside. They're supposed to be added by this proxy. One of the things that James Kettle suggested were also to add these headers as a part of the cache key. Because if we add them to the part of the cache key, then the benign client is never going to send those headers, and so the client is never going to get the poisoned version. We should, of course, also fix the server-side application, which in this case allowed us to inject bad code on the server based on a host header. Yeah, I have a couple of more minutes. I'm going to show you one last thing that I discovered recently. It's something called, where we're going to look at data APIs. So how many of you are familiar with GraphQL? Quite a few of you, yeah? So GraphQL, it says, GraphQL is a query language for APIs and a runtime for fulfilling those queries with your existing data. So we can now create like these magic REST endpoints where we can query and get all kinds of data instead of having to specify every message. And this is really cool as a developer because we don't have to specify all the endpoints, and we can get the data, the exact data we need, et cetera, et cetera. But if we're not doing this correctly, we might also end up with data leakage, authorization issues, things like that. So this is actually real stuff. This is not GraphQL, but the first one here is, I saw this once when I was doing a security test. Script.asp query, and then the SQL query. So this is SQL injection by design. And same thing, this was a web service where they would take an SQL query as a part of the SOAP message and then execute that and return the result back. And this is the kind of stuff that we can end up with if we're doing GraphQL the wrong way. Because we can be able to access things that we're not supposed to be to access. We can get access to data that belongs to other users and all kinds of stuff like that. A couple of examples. This was from HackerOne, and this was actually on HackerOne. So it wasn't just a program on HackerOne, but it was HackerOne that was hacked in this finding here. And so they have this issue where by using GraphQL, you could traverse some links between objects, and then you were able to grab data. But a better one that I found the other day was this one, verify.shopifycloud.com. GraphQL discloses internal bear consumption. And one of the comments said, if you can escalate this to bear denial of service, that would be devastating. Yeah, so this is a bunch of links. I'll tweet these out later, so you don't have to photograph them. You can get them in a format where you can actually click them. But a lot of people have been doing a lot of research into this. I'm merely the conveyor of this information. Like there's a couple of guys who made something called WISO Serial, which is a lot of listings of vulnerabilities in terms of deserialization attacks. You have XSLT stuff, like in here you have template injection. Once again, that's James Kettle behind that. You have the links to the subdomain takeover stuff. You have the links to Nicolas Gregoire's presentation on SSRF and some YouTube videos, et cetera, and things like that. So that's it. There is a URL at the bottom here. If you want to play with some of the demo stuff that I just showed you, like XXE and insecure deserialization, there is a GitHub repo there. It's github.com/Oftedal/deserialize. And you can get that app running as a Docker container. And in the GitHub repo, you can also see like the payloads that you can send it to attack it. So that's pretty well on time. So thanks a lot for coming.